You should be able to see my screen now, yeah? Okay.
Thank you.
So yeah, like I said, so the demonstration, like last time you remember that we talked about, we had your lottery that we were implementing. And what I wanted to do when I wanted to move it to Haskell was when I wanted to make it kind of arbitrarily sized, so you could make it work for any number of people. So I've taken a slightly simpler example to go through, although there's actually plenty of complexity in here to make it interesting. So the simple example I have is, the idea is, it's like a church collection, right? So, you know, a bunch of people go to a church and they all put some money in the plate, and then the church gets it. So it's a very simple idea, but the main thing that I want to do is show you how you can write a Haskell program that can generate that basic contract for any number of people. So you can have one for 3 people or one for 1,000 people.
So, but I mean, you could also look at this as it's really a contract to like take an offering. So you could take an offering for anything really.
Yeah, that's right. I'm just using church collection because when I was there, what it is a number of people pay into an account and then one account takes it all away. Right. That's it can be anything. It just some kind of multiple.
No, I like your reference
into one, but yeah, I don't know.
But I like to think of this. So this really could be repurposed as like an offering contract to one wallet.
Yeah. And this same idea is going to apply to our lottery in a very, very similar way. But I just wanted to simplify it slightly and have slightly fewer steps.
Cool beans.
So this is a program and we'll go through how it works. But I'm just going to generate the 1-person contract so I can show it to you in Blockly and then show you how it grows. And then we'll go into how the Haskell side works. So I'm just building that for 1 person. We'll send this to Blockly. So that's our Blockly contract, right? So person 1 deposits 1 Lovelace. In this case, I've just left the amounts simple because it's not something, you know, all of these things can be more complex, but I'm just trying to keep things simple. So person 1 deposits 1 Lovelace and they pay it to the church. And that's it. That's our contract. Okay. So we can send it to the simulator and that works as we expect. So we deposit 1 and then it gets paid to the church and we are finished. So let's run this.
Just like a donation.
Yeah, it's a donation. Now, what I want to do is run this with 2 people. I'll explain why I type in 2 twice in here, but just bear with me for now. What I'm actually going to do is build up from scratch, but I just kind of wanted to show you how the finished contract works. So you can see this one's a bit bigger, and we can send it to Blockly. So now we've got person 1 deposits and pays it to the church, and then person 2 deposits and pays to the church, and then we're finished. So again, if we simulate that.
And that could run on and on and on until like a time period, or?
Yeah. So
what would ultimately end this happening, or this could happen all the time, or?
So what the idea here, you got to remember that these Milo contracts are finite things. So what you can't do is have an infinite loop that just says, you know, while people are donating, pay it to the church. And there's a good reason for that. That is to make sure that every contract eventually finishes, because that's important, because it's at the end of the contract that everybody gets their money. So what we're doing is we're writing a program that can give us a contract of any size, right? So what you might do is say, you know, 10 people are attending to the church. Give me a contract where they all make a donation. And then this, just to make it simpler, this is 2, right? So it's the Haskell program that has the generality that that can apply to any size, but then the Milo program still has a fixed size of a fixed number of people.
Okay.
if that makes sense.
I got you.
So I'll quickly reset my simulation here, and then
So this would be a time-based offering or donation.
yeah. So if you look at it, I'll go back to Blockly. If you look at it carefully, person 1 has to make their deposit after 10 slots, and then person 2 has to do it after 20 slots, and so on. So there's a fixed amount of time for each person to make their donation.
Gotcha.
Yeah. Like I said, I don't want to over focus on the details of whether this actually practically makes sense. It's just what I really wanted to demonstrate is that we can generate this for any number of people, right? So this is generated for person 1 and person 2.
Yep.
And then,
I got you.
yeah. And then we can make them really big, right? We can go, well, I've never tried 100, but let's try 100. It should work.
I feel like though you could even make cool things with just this simple contract. I mean, you could fundraise for a startup. You could
Yeah.
help your neighbor get a surgery.
Yeah. Yeah, definitely. Or you could buy something together with a group.
Yeah.
Like, yeah, it doesn't even have to be a donation. It can be it can be a group purchase or something. Right. So I've done it with 100, so this is really big now, and you could never do this in person. And if we send it to Blockly,
it's going to be crazy in Blockly.
I think we're going to, oh, wow. Okay. Good on Blockly. It works.
Could you imagine trying to make that in blocks?
No, it's impossible. Like, you could, if you do 10, it's tedious, but you can do it. But the bigger.
And that's the principle of what we're learning today is how to make this in Haskell, so you can keep it clean and simple.
Yeah. So you don't have to build up these huge structures by yourself. Especially because I know, like, with your lottery contract that you're ultimately building, it's not fixed to a number of people, right? You have to be able to generate it for the right size.
Yeah.
So yeah. Anyway, I'm not going to run the simulation for this one because it just involves 100 clicks, which I'm not that keen to do. So what I'll show you is a brief overview first, and then I'm going to go into some detail about how all of this works, right? So feel free to ask questions, but don't feel the need to understand completely what's happening here because I don't expect you to. Okay. So what we have is we have a function called contract, which takes 2 integers, and I'll get to why there's 2 and not 1 later, and it returns your contract. So when it's generating a 0, like when you get a 0, like, so when you're trying to create one of size 0, then you do just a close. Okay, that's like the simplest possible case. And otherwise, for some number n, we build this contract, but the key thing in it is that this is kind of doing we make one of these steps for person name, paying to the church, and we follow up by the contract for the n-1 people. So this is a concept called recursion, which we're going to talk about today.
Gotcha.
First I want to show you some functions with strings because we're going to need them. So I've just got the Haskell REPL here. We used it in the first lesson, if you remember.
Yep.
So if you remember, we can. Well, I'll write it here. So you can say, like, A is a string, and A is equal to hello. I'll just put a comma after it, and then we can say B is another string, and B can be equal to boon. Okay, I think if we hit run, or reload. Okay, reload. Don't worry about run. Just, yeah, you should be able to. So if we type A into the REPL here, we get hello, and B, boon. So that's just, how you have values. So the value of A is hello, the type of A is string.
Gotcha.
Okay. Now, there's a function, or if you like to think of it as an operator, which is written as plus plus, like that. So to join two things together, we call that concatenating. So to join things together, we use this plus plus operator. So for example, you can have A plus plus B. Well, I'll do it here. And that gives you hello boon.
Yep. Okay.
Right? So it's just sticking one onto the end of the other. So that's the first function we need on strings. So we can say, apple plus plus pie, apple pie. Yeah. So
and this relates to the recursion.
No, there are actually three concepts we have to cover, and the recursion is the last one. So
Okay.
What this is, why I'm showing you this, is because you noticed in the contract we've got Blockly. We got person 27, person 28, person 29, and so on.
Oh, okay.
So we need to append the number to the name. That's why I'm showing you that part.
Yep. Now it's clicking.
Yeah.
Thank you.
Yeah. Good point. I'll show you why. Okay. The second function we're going to need is called show. So what show does is turn things into strings. So I'll just show you some examples. So if you call show with a string, it just returns string in quotes, so that's not too interesting. But if we show, say, the number 4, it returns you the string containing the number 4. So what we use with show for is to convert things into strings. So gotcha. Again, why are we doing that? Well, because we might have a person number, which is an integer. Person number can be 3. Then we can try do it and then I don't know, person can be a string, and we just say person equals person. What am I doing here? Okay. So if I try to say person plus plus person number, you see we get an error. Could not match expected type char list. And I'll just tell you just quickly, when you see char list like that, that's just the same as string. I don't want to go into this lesson about why, but just when you see that, think that.
Gotcha. And I remember you explaining about, putting integers and chars together. Yeah.
So they don't, right? So this is why that doesn't work, because plus plus expects 2 strings, not an integer in a string. But so that doesn't work. But if we do show on a person number, so show person number, that gives you a 3. So that means to join those together, we'll say person plus plus show person number.
I gotcha.
And that works. That gives us what we wanted.
And then you're using the recursion to update that number every time.
Yeah, exactly.
Nice.
So we've got the plus plus and we've got the show. There is another function that I want to do, but we'll get back to it later, okay? The reason, let's just get back to the final function that I want to show you later, because it's going to be a lot more useful when we see it in the actual contract. So that's the first thing I want to show you, the few string functions.
Yeah, thank you. That's helped me understand what's going on in the contract in the Haskell.
Yeah, you'll need that. So the second thing I want to do is show you this where syntax. So let me come up for an example. So for example, you might say something like A is a, let's say we have we'll stick to this person and number thing, right? So you might write something like person with number is equal to person. So I'll get rid of this person number for now. So we've got person, which just means person, and then we say person with number equals person plus plus show 3, for example. And that works. That's just what we did before. But you might want to separate the show 3 into its own separate definition. So you might want to say, like, instead of person plus person number, and then there's this command where, not command. I'll say syntax where person with number equals show 3. Right, so you have an expression like that. So what that means is that person is 3, and that's coming from the outside here. But person with number is kind of part of the definition here that comes under this where. So first of all, I'll show it to you working, and then so reload. Cool. So if we look at person with number, have I just misspelled it, or? Yes, I don't even know how I respelled it, but never mind. Hey, there it is. So it's person 3, just like we expected. But what I've done is I've done this where, right? So I've used some name, and then I define it below under where. Okay.
And you can add that the where into any part of like one of these expressions.
Yeah, into an expression or into a function. Yeah.
Okay.
So notice that if I write person here, we can see it because it's up here. But if I write, sorry, I've made this confusing. I'm going to call this num and this num, so it doesn't conflict with this outside thing.
I got you now.
Yeah. Okay, so that's num and that's num there. So let me just reload it. Yeah, so that gives us person 3. Yeah. But notice if I type num, that doesn't exist from out here, because num is something that only exists during, like, inside this expression. So this where only applies to this. That's really important. So if you're building up some big expression and you want to give something a name, but you don't want that name to be visible from everywhere. That's what you do. You use where. Okay.
Gotcha. Yep.
Cool. So that's that. Where form is another thing we use. So we will. I'm going to leave it at that, but yeah, essentially we use that in our contract, so that's what it means.
Gotcha.
Okay. Finally, recursion. This is the one I want to spend a lot of time on because it's mind-boggling. There's a joke that says, in order to understand recursion, you have to understand recursion.
Oh, I like it.
Right? So you end up, so what's...
Very enlightening.
Yeah. So what recursion basically is when you define a function in terms of itself. So I will show you a really simple example just to start with. So what we're going to do is we're going to write a function that takes, so something like, I don't know, well, I'll just call it f because I don't know what else to call it. And it takes an integer and it returns you a string, right? So we've seen integers and strings before. So what I want is, for example, if I give it, like if I say f5, then I want the result to be 5, 4, 3, 2, 1.
Okay.
If I give it 3, then I want the result to be 3, 2, 1. And
okay.
So, yeah. So what we do, and this is how these recursive cases always look like this. So I'm just going to show you an example, but sorry, let me just hang this up. Yeah, so essentially we have something called a base case, and then we have the general case. Sorry, my phone keeps ringing.
That's all right.
Okay. So the base case is with a special case. So in this case, the base case is going to be like when we give it a 0, then we just return an empty string. Okay, so that means if we say f0, that's just going to give us an empty string.
Okay.
Nice and easy, and we can already test that part. F of 0, empty string, right? You notice if we give it anything else, it crashes because we haven't used it. So now we do, so this time we've specified a specific, like this definition of the function only works for 0. Now we want something more general. So you say fn. Usually when you were talking about an integer, you can call it n, but obviously you can call it anything else.
Okay.
So what does fn, what's that going to do? Well, the first thing we want to do, right, say if n is 5, is we want to print the number 5. So, or not print, we want to return the string 5. So show n might be a good start, right? That's just what we used before. Remember, show turns us from an integer to a string.
Yep.
So if we go f5, that's just giving us a 5 for now. But then what we want to do is append that to 4, 3, 2, 1. So we show it, and then we append it to f of 1 less minus 1, like that.
Okay. Yeah, I'm see where you're going.
Yeah, so it starts off, so what we do is we call f, and we show it with n, and then we call the same function with n being 1 less. So that means it's 5, and we go output of 5, and then we append that output to the result of calling this with 4, which outputs a 4, and then appends that to the result of calling this with 3, outputs 3, 2, and 1, and then the next one after 1, and then we end up with 0, which ends up in this case, and we terminate.
Gotcha.
So f of 5 now gives us 5, 4, 3, 2, 1, like we said.
And is this so this n equals -1? Would that also be, is this the similar function you'd use to change instead change it, or is this that's a different function we're getting to? How ours is like each person donating to the contract was person 1, 2, 3.
Yeah. Oh, instead of 3, 2, 1, you mean?
Yeah.
Yeah. Okay. Great question. So yeah, let's do that. Let's fix this string. So instead of 5, 4, 3, 2, 1, we want to go to 1, 2, 3, 4, 5, basically, right?
Yeah, and but what I'm asking, is this the way that you would do it, so that
Yes.
they would be person 1, person 2, person 3?
Yeah, this is exactly how we do it. And in fact, what we're going to do now is update this same function to go backwards, to go forwards, not backwards. Gotcha. Because this exact logic ends up being applying to our contract.
Very cool.
So instead of going from 0 from n to 0, we want to go from 0 to n. Now, the way recursion works is you usually build up from, like, you recurse up from bigger things down to smaller things. So our base case is still going to be 0, and we're still going to do this n-1 until we get to 0. But what we have to do is kind of work out how far along we've gone and subtract that in order to get to like how we go. So what I'm going to do is add another parameter to this function. So it's going to take 2 integers. And so I'll call this one like max, not max, actually. I'll call it something, total. I don't know what to call it, total. Like, that's going to just give us so the way we're going to call it is like, I'll just write the code and then explain it, actually. So what we have to do is, instead of showing n, we have to show total minus n. So if we're doing it for 5, then total is going to be 5, and we're going to start with, like, and this n is going to be 5 as well at the first time, and which means 5 minus 5 is 0. So that's our first number. Actually, okay. We want to add 1 to it because we want to start with 1. And then what we do is we just pass that total along to the recursive call, like that. So that total never changes, right? It's just passed in to remember what our total size is. Okay. So what that's going to do is start with 1. So remember, n is 0 here, so we're doing, sorry, n is 5 here, so we're doing 5 minus 5 plus 1 gives us 1. And then n is going to be 4, which means we're going 5 minus 4 is 1, plus 1 is 2, and so on, right? So the point of this is to remember our total size so we can do that subtraction and go upwards instead of downwards. So if we go F55, what have I done? One, two, three, four, 5. So I will quickly go back to the contract to show you that this is exactly the same logic that I've used to generate that person 1, person 2, person 3, person 4, okay, type thing. So if we go to the Haskell editor here, you see it takes 2 integers. This time returns a contract, not just a string. Yep. And then when it's 0, then we return just a closed contract. That's like the equivalent of our empty string and the other one.
Mm-hmm.
And what I've used is here, I've used the where. So I've done, the person number is, okay, so our second parameter here was num people, and n was our recursive parameter. So I've done the same thing, num people minus n plus 1. And that's the same as total. I mean, I can call this num people here, just like that. It's the same.
Yep, I'm tracking now, and now I see why you explained all this up front.
Yeah. Because otherwise, if we start talking about the contract and we get into the nitty gritty of this, then it's just it becomes.
Yeah, then I wouldn't understand any of the. Yeah. Thank you.
So there's method to the madness, And the other thing you'll see I've done in my contract is in this kind of definition here, we match 0, and then we get this other parameter num people, which we don't use at all because we just return the empty string here. So you can, instead of naming it here, you can just say underscore. That's like I know there's a parameter here, but I don't care what it is. So that's what that ends up looking like. We can't do that. Sorry. We've got to actually fix this here to num people and total. Like that. So you see what I've done? I've just renamed that thing to num people, and in this definition with 0 here, I've made it an underscore because we can ignore it. But if you find that confusing, we can leave it as well. It doesn't matter. It's just that we don't use it in this expression here.
Gotcha.
Yeah. Cool. So so now if we say F66, it does what we expect.
Yep, I gotcha.
Cool. So I've got the code over here, but let's build it from scratch, because I think
yes,
now
please.
We've covered all of the concepts. Let's build it from scratch. So what I'm going to do to start with is undefined is useful because you can just, when you leave things kind of semi-complete, you can just write undefined. So what I'm going to do is, I've created a function that takes an integer and an integer to a contract, and I've handled the 0 case because it's kind of not interesting. So when we pass it as 0, it just returns a closed contract.
Yep.
Now let's go to Blockly and let's clear it. What have I done? I thought I cleared it, but I might have. Hang on, I'll go to the start.
Delete 1,301 blocks.
Yeah. Okay. Yeah. Cool. So what we're going to do is do something really simple. Just build it up for one.
Did that get rid of that other side contract that was in here?
That's what I'm wondering.
Can you zoom out that thing to see?
Oh, there we go.
Yeah.
There it is.
I thought that was going to cause a problem. I think there's 2 different contract blocks now up there.
Can we reset this somehow? I'm just going to reload and hope for the best. So
I think that's the safest way to start.
Yeah.
Yeah.
We're okay.
Nice.
Okay. I don't know how I must have clicked something to duplicate it, and I'm not sure what I did. Okay. Anyway, so let's just build up one of these contracts real quick. When there's a deposit by that was a party, right? Here. We'll call this person 1. The amount of one token ADA. There's actually 1 Lovelace, as we just covered. into account with owner person 1, and then we'll continue with a pay contract where the payee is, well, actually the church doesn't need an account. I think in the previous one we didn't have it, so I'll just payee can be a party with a role, church, the amount of 1 ADA from account. Whoa, I've just discovered a bug in our contract, actually. I think I discovered a bug in our contract. So I'm just going to make this account 1, and then we're going to pay from account 1, so person 2 can pay from account 2, and so on, right? And then we close. And after slot 10, we also close. Right, so we've done more complex things than this before. This is straightforward. So there's a deposit and we pay. Okay, we sent to simulator, and we take this and we paste it into our Haskell code. Just like that.
Gotcha.
Okay. Right, that's not recursive yet, but this is our starting point. So this should compile. Yeah. Not particularly enlightening, right? It's just
simple use case.
Yeah. So now we want to do a few things. So first of all, so there's 3 things we have to change, right? Let's do the recursive one first, because it's kind of the interesting one, right? And then we're going to build up. We're going to fix all these values up first. But first, let's do the recursion. So in Blockly, right, when this contract was finished, we did a close. But in fact, here, instead of just always doing a close, we want to do a recursive contract in this part here. So if you look in the Haskell editor, that's this part here.
Gotcha.
And I'm just going to put some brackets in so Haskell doesn't get confused. And we're going to pass in a contract n-1, and num people just stays the same. Okay.
And it's kind of just the repeating what you've got declared up top.
Yes, that's right. So like the 0 case is handled for us. It's just a close. So what we do here is we repeat it, but with n being 1 smaller, which means that now we're going to repeat this until n gets to 0, and then ends up being it ends up terminating, and then we get our contract. So if I run that, actually, I want to run it with something much smaller than 100.
Yeah.
I'll just recompile. Right, so we got person 1, and then we've got person 1 again, because we haven't fixed that part. And then we go pay, and then finally we close here.
Yep.
I'm not going to put this one to Blockly because I want to carry on fixing this stuff. Okay, so I'm going to put in a where, and we just have to start pulling out these things. So
why does the where go outside of the close?
Yeah. So
what prevents, how does that take place before the contract closes?
Yeah. So remember that this whole contract is just a value, right? So this where is part of Haskell, not part of the contract, right? So if we go a simple example,
the where is not part of the contract. That's what's important for me to grasp.
So this is the value, and this is like the where clause, which is the
part of the code.
The code, yeah.
Thank you.
So what we'll do to start with is we'll just say I want to like a name which is I'll just call it n counting up, right? Meaning, instead of being 2, 1, 0, I want it to go 1, 2, 3.
Yep.
So that's equal to num people minus n plus 1. So we've seen that logic already. I've just put it here now. So this is my definition. And now what I can do is actually put it into a few places. I'm not going to touch these strings yet because there's a little bit more complexity, not much, but we have to do that concatenation that we were looking at before. Yeah. But what I'm going to do is make sure that these account IDs are correct. So instead of 1 here, we're going to have n counting up here and then here as well, right? So when the person pays into account ID n counting up, then we pay from that account ID to the church. And I think we've built up enough complexity now that I just want to show it in Blockly quickly. So if we send that to Blockly, we've seen now, so when there's deposit into account 1, from account 1, when there's deposit into account 1, then we pay from account 1. And then when there's a deposit into account 2, then we pay from account 2.
So the account's updating in this Blockly example, but the person is still the same.
That's what we have to do now.
Okay.
So yeah, I'm just kind of really trying to go one step at a time.
No, I love it. I love seeing each piece come to get together.
Yeah.
Thank you.
Cool. So what we have to do is we have to say, person name is equal to person plus plus show n counting up. And this is somewhere where I was stuck. So what I'm going to do is I'm going to replace those person names, and then we're going to get an error. And then I'm kind of just going to tell you what the solution to the error is. So when you see it, you can do this. But explaining exactly what went wrong and how it came about is a little bit beyond the scope of this. And I hate to do that, but
no worries.
Yeah, different things require different levels of understanding, and I really don't want to go into overloaded strings and type classes. So just trust me that, I'll show you the error and then I'll show you the solution.
Cool beans.
So what we've done is everywhere where it says person 1, we'll say person name instead. Cool. So that's going to give us a strange error.
I noticed when you're writing this in Haskell that the parentheses are no longer part of the code. When you replace person name, it used to, have, quotes.
Yeah. So quotes are not, because when the difference between
quotes is what I meant. I'm sorry.
Because the quotes are here, right? So we've built up a string here, but then here, that's a reference to that string. Yep. So the quote, when you're in quotes, you're talking about a value itself. Whereas when you're in when you're not in quotes, you're talking about the name that you've given to some value. So this is, you can see that this is complaining, and it says could not match expected type token name with actual type char. So what it's saying is it expected a token name, but we gave it a string. And that's a confusing error. Now, first thing you've seen, well, you haven't probably noticed it, but one thing I've got here is I've got an import of data.string in this contract. That's quite important, and I'll tell you why. So just really briefly, you know how we had show, which takes us from a value to a string?
Mm-hmm. From an integer to a string?
Well, it's, yeah, it's
any
from
value.
an integer to a string, but show is what we call polymorphic. So it doesn't just work for integers, it works for like anything that can be turned into a string.
Nice, okay.
Yeah. So I'm telling a small lie here, but I think for the sake of understanding, it's okay. There's an opposite function, which is called from string. That turns value into, that turns a string into whatever it was supposed to turn into. In this case, token name. So just remember that if you get a problem saying expected token name but got string, the solution is to call this from string.
Yeah, it fixed the error.
Yeah, it fixed the error. So that's really important.
Very important. Thank you.
Yeah. So look, just think of it as being the opposite to show. It's not strictly correct, but that's as far as we're going to go in terms of explaining it. Because I think in order to understand this, you need to understand like all of Haskell. So take the shortcut. Yeah. Cool. So now we should be done, right? So we've got person 1.
Yep, updated.
Person 2.
Yep.
2. And let's simulate it. Right, so it's asking person 1 to deposit. There's something else that's not happening, which we'll get to now. Asking person 2 to deposit. And then if we look at the logs, the contract paid to Ada to the church. So that's kind of what we wanted to achieve. There is one small thing, which is this warning. Timeouts should always increase in value, right? So if this has to be complete by, sorry, I'll go to Blockly to look at this. So if this outside bit had to be complete by slot 10, then this inside bit should be sometime after slot 10. And so on.
I got what you're saying. That actually brings up a question I had about this contract. So could, if there's a time after the first person, deposits $1, is there how does it work to just have like the contract itself, maybe say have a 15-day expiration period without first saying, how does that work? The whole
as far as I understand, it's a really good question. So as far as I've understood with these Milo building blocks is you can't. So you have to set a specific timeout for each action, and the whole contract is basically like the whole contract finishes by the latest timeout, and that's kind of all it is. So if we make this 20, then essentially, because this is the latest one, the total timeout of the contract is 20.
So sorry to interrupt.
Yeah, go.
I was going to just say, so would it technically be able then to dynamically update the slot number? So here's my where I'm looking at this contract, thinking about it. I have a 15-day fundraising campaign,
Yeah.
but whenever someone donates to the contract, I don't want the next donation to be timeout based on that donator's donation. I want it to still have a 15-day timeout period.
Yeah. So one thing we could do is we could right. Okay.
You see what I'm saying?
Yeah.
Yeah,
So
like
yeah. So you want okay, there's two things here, I think. One is that if there's a let me just think about it. So I think there's two aspects to it. Yeah. One is that for any specific sequence of donations, like person one and then to person two, if the total number of their timeouts has to be equal to your 15 days, right? So
yes.
I mean, if you got two people, then essentially, one has to put in the money by 7 days, and then the other one has to put in the money by 14 days. Sorry, not by, but the first person has up to 7 days, and then the next person has up to another 7 days. Even that's got a little bit more complexity because, of course, there is a scenario where one person puts in on day 13 and the other person puts in 1 minute after them, and that's still fine. So let me get back to you. I'll tell you the two observations that I have about that, and then maybe in the next lesson we can extend this contract to
cool beans.
Carry. Like, I haven't quite worked it out in my head, but I think there's two things. Like, one is that the total amount of time has to add to the total contract expiry time. So that means that we've got two people, they get, the first person gets 7 days, the second person gets, so first person has to complete within a week. Second person has to complete within 2 weeks. But there's another thing that in most of these cases, it doesn't actually matter which order they do it in. Right? So you could have person two put in first and then person one put in second. So this is where you get a bit of a combinatorial explosion where you essentially have to go instead of just having this one when, you have to have a multiple whens. So we've got like when person one makes a deposit, then we kind of go through this thing, but we can alternatively put another deposit where person two makes the deposit first and then the person one follows up. So I think the way we ultimately generate these contracts is we're going to have to kind of generate all of the combinations of the orders that the people can do, the permutations of the orders that the people can do it in.
Gotcha.
And like, we're not going to get that done today, but that's the idea.
No, we're coming up on time now almost.
Yeah. So I wanted to just fix these slots according to how I'd originally planned it, although I think you've brought up some really good points on.
Will you go back to your
the
first, because I'm just looking at that for a second. I'm really starting to put the blocks together in my mind.
Yeah. Okay. So the final change that I'm going to make to this is, right now this contract just has 10 as that timeout. So instead of just having 10, I'm going to have the person number times 10. So the first person has to do it by 10 steps, and then the second person has to do it by 20 steps, and so on. So that's just that, like that.
Gotcha.
And that's that recursive contract really then. So what we've done is, well, what have I done? Oh, could not match type integer with slot. Okay. So, okay, again, what I've done here is it didn't like just being passed an integer here because it expected a slot. So,
I track, and I see what you did.
yeah, so I called the slot constructor, which gave it an integer. So that worked. It's just like, so here for person name I used from string, whereas here I used I called slot directly, and I knew to do that because I experimented with the other ways, and this worked. But I think like what I'd really like to go into next time is learn a little bit about making our own Haskell types, so that we can see how we might, what the structure of something like a contract or a slot is and what that actually means. Because at the moment, it's just like a language that we're just speaking. But what I want to talk
That would be
about
awesome.
how we might define something like this in Haskell, and then we'll have the full answer to something like slot, and we won't have the full answer to from string, but we'll have a more complete answer than we have right now. So, yeah.
That'd be awesome.
So what I'm going to do is I'm going to stop recording.